Okay, mathematical induction. So what is this about? What's the point of this? It's directly related to sequences in series, and it's just a way of it's a technique of mathematical proof that enables you to prove the validity of a statement over a positive set of integers. And so really what you'll see is the reason for presenting this in an algebra book, on the sequences in series section of an algebra book, is because we had talked about this in a previous video, but if you have any kind of random sequence, this doesn't have to be arithmetic or geometric, just completely random. You don't know what it is. So this is an a sub n. Okay? You can make an attempt at finding the summation, the partial sum, or the summation formula S sub n for this sequence by saying, okay, the sum of the first term is 2. The sum of the first 2 terms is 9. The sum of the first 3 terms is 9 plus 16. The sum of the first 4 terms is 41 plus 25. The sum of the first 5 terms is 73 plus 66. Okay, so but what you have here is a new sequence, which you call S sub n. So if you see S sub n, you know it's related to it's a sequence that's related to an a sub n. And what you can do is, and there's previous videos where we do examples of this, but you can try and find you can look for the pattern, like you can develop the S sub n by just analyzing the terms of the sequence, right? We do that. We derive an a sub n for presented sequences. You can do the same thing, and you'll get something. You'll get an S sub n. You'll get some function of n. Okay? But the problem is that you can't say that S sub n is true right off the bat, because it's only true for the whatever terms you use to derive that formula. How can you say it's true for the 100th term, the 500th term, the 5,000th term? Because for arithmetic sequences and geometric sequences, when we got those S sub n's for those sequences, we had to prove it. So how can you prove it? Like, how can what's a general method we can use to try and prove an S sub n that's found? And that's what mathematical induction does. And so what you do is you first prove that, like, let's say the formula, we have an a sub n and we come up with a p sub n formula. So I'm not going to say S sub n because it doesn't have to be necessarily a summation. But if we have a p sub n that we came up with, you first want to show that p sub 1 is true. Then you want to show that the truth of p sub k implies the truth of p sub k plus 1. And so that's a little confusing. I'm going to show some examples real quick, and you'll see what I mean. But also just note that you can do the same thing. Like, you don't have to start at p sub 1. You could prove it for integers that go from j to k, like from 10 to infinity, right? Like, so you don't have to go from 1 to infinity. You could say it's true from 10 to infinity. You don't have to start at 1, but this is just positive integers, though. We're not talking about integers that negative integers or 0. But let me show you some examples, and this will clear up how this works. So let's say we have the sequence. Okay, that's the sequence a sub n. Well, first of all, let's write what is this formula? Let's derive it. We've done this. We did this in videos in the past. So this looks to be an arithmetic sequence where you're adding 2 each time, right? Okay, so we know how to write out an arithmetic sequence. We say a sub 1 plus n minus 1 times the common difference. So 1 plus 2n minus 2. So you've got 2n minus 1. That's the a sub n formula. Okay? So now we already know the formula for an arithmetic series, the S of n for an arithmetic series, but we're going to use this induction method. In fact, we showed how we can prove, we showed how we could derive the formula for an arithmetic sequence, the S of n, without even using induction. And we did that, but we're going to do the induction method for illustration. Okay, so let's say this wasn't an arithmetic sequence, and we're wondering, okay, what is the S of n for this? For this is just a random sequence. So the sum of the first term is 1. The sum of the first 2 terms is 4. The sum of the first 3 terms is 5 plus 4. The sum of the first 4 terms is 16. Okay, and this is our S of n. Okay, now we can do the same thing, but let's derive the S of n. Okay, so we add 3, then we add 5, so it's not a arithmetic sequence. Well, 4, 9, this is, so 1 squared, 2 squared, 3 squared, so this is n squared, right? I mean, so starting at 1 squared, then 2 squared, 3 squared, then 4 squared. Okay, but yeah, that's true for these first 4 terms, but how can we prove that this is true for, term 10,000? So to do this proof, like this first step's going to seem kind of pointless, but this is like how you do the official proof. Okay, show that S1 is true. We're dealing with S here. So S1 is, so plug in 1 for n is equal to 1, and yes, so when we plug in 1 to our formula, we get S of 1. Okay, that's step 1. That's easy. Okay, next we assume that Sk is true. Okay, so write out Sk. You would have 1 plus 4 plus 9 plus 16 plus, okay, and then, right, because this sequence, we're adding all the terms of this sequence, so this 2n minus, or this would be 2k. Right? This is the last term of the sequence, but we're adding them, and this is equal to k squared. Okay, we're changing from the index n to k for the proof. Okay, so if we assume this is true, can we now show that S of k plus 1 is true? Let's write out S of k plus 1. 1 plus 4 plus 9 plus 16 plus, okay, and so what we do is we'll say we get to, so 2k minus 1, right? But then we go to the k plus 1. So that was 2k minus 1. That was at k, but now we're saying 2k plus 1. You see? Right? S of k plus 1 is S of k, including this, but now just substitute k plus 1 in here. And then this would be equal to k plus 1 squared, right? Like the n squared, just substitute in k plus 1. Okay, so again, we've assumed that this is true. I know this is a little confusing math jargon, but this is how you do it. We've assumed that this is true. So that means that this is equal to k squared, right? Because we just first rewrote this and then we added the k plus 1 term. Okay, so now let's simplify this. So you've got 2k plus 2 minus 1. So 2k plus 1. Okay, so k squared plus 2k plus 1. Can we factor that? you've got k, and then a 1, 1, right? K squared plus 2k plus 1, which, so the left and the right are equal. So it's sk plus 1, we've proven it. And that's it. That's how you do it. Okay, let's do another one. Now, this is, we're mainly doing this to prove, like when we derive an S sub n, a summation, but it doesn't have to necessarily be a summation. It's really anything. If you find any, if you come up with a formula for any sequence that comes, it doesn't matter where it comes from, and you want to prove that it's true for all integers, then you'll use this, all positive integers. But we're mainly focusing on you know, what we're studying is summations and calculus, summations going to infinity. And so we're really, this is really about summations here. Okay, so let's say we have the sequence. Okay, that's a sub n. Let's try and derive an S sub n and prove that it's true. Okay, so what is the a sub n formula? All right, so 2 times 3 equals 6. 6 times 2 equals 12, so no, it's not a geometric. 2 plus 6, or 2 plus 4 is 6, 6 plus 4 is 10, so it's not arithmetic. So we multiply 2 times 3 and get 6. And then we multiply 6 times 2. Okay, what else can we see? What kind of pattern can we see here in the denominator? Okay, so we multiplied 2 times 3 and got 6. Well, okay, if you look, this is 1 times 2. This is 2 times 3. This is 3 times 4. Okay, so you see that pattern? You know, if you factor or separate out the multiplier, so what you have is the term that you're on, n, times n plus 1. You see? And the third term, you would have 3 times 4. Yeah, okay. All right. So that's a sub n. Now, what about s sub n? Okay, so the sum of the first term is 1/2. Then 1/2 plus 1/6 is 2/3. Okay, then 2/3 plus 1/12 is the sum of the first 3 terms, so 3/4. See, this is a potential S sub n. Okay, what would be the formula of this formula? So it looks like you would have n plus 1 in the denominator and n in the numerator. Okay, so we just need to prove that this is true. To prove that this S sub n is right for this sequence, we need to prove, use mathematical induction, right? In this case, this isn't an arithmetic sequence or a geometric sequence. But we would need this to be, we would need this to be an arithmetic or geometric sequence. Then we would know what the S sub n formula is, and it's already been proven. But this is neither one of those, so we need to prove it. So okay, step 1: prove that S of 1 is true. Okay, and we're saying S of 1, but again, this doesn't have to be a summation; it could be anything. P. That's why the theorem in the book I'm reading out of uses P, because it can be. It doesn't have to have the meaning of a summation. Okay. All right. So S of 1, according to our formula that we come up with, is 1 plus 1, and then in the denominator, and then 1 in the numerator, 1/2. Here we show it's 1/2. Good. Okay. Okay. Now the second step. Okay, we're going to assume that S of k is true, and this would be equal to 1/2 plus 2/3 plus 3/4 plus, and then the last term would be this k okay, and then this is equal to okay. So now what is s of k plus 1? So that's 1/2 plus 2/3 plus 3/4 plus okay, plus, so k plus 1, okay, and then what? And then k plus 1 plus 1, so k plus 2, right? And then now k plus 1 plus 1, k plus 2, all over k plus 1, okay? This is s of k. So this is k over k plus 1. So now let's add up k over k plus 1 plus 1 over k plus 1 times k plus 2. Okay? So this is equal to, so we would have, making the common denominator, we would have k times k plus 2 all over k plus 1 times k plus 2, right? Plus right? So what we have is we can add these two up. So let's distribute this. We've got k squared plus 2k plus 1 over okay, so let's factor this. We got k 1 1, it's k plus 1 squared okay, we cancel out a k plus 1 and you get, and there you go, that equals this. So we've proven that. We've proven that if this is our a sub n, then the s sub n is in fact this for all positive integers. Okay, here's an example where you were not proving a summation. So let's use mathematical induction to prove that the number 4 is a factor of 9 of this. So we've got so is 4 a factor of any n here? So n is equal to 1. So a sub n is equal to 1. 8. N is equal to 2. 80. N is equal to 3. Okay, seems to be the case. 880, I'm sure 728. Yeah, it is because the 8, right? 728 divided by 4. Yeah. So what we can do is say, okay, what the statement we're trying to prove is that we're saying that this here, this expression, is 4 times some positive integer. Well, let's call this C. Okay? If that's true, if any n you plug in is equal to 4 times some positive integer c, then that the statement is true. So step 1 is p of 1 true, right? I mean, this is what we're saying is p of 1 true here. So like, okay, so a sub 1 is equal to 9 minus 1 is equal to 8, which is equal to 4c. 8 divided by 4 is 2. C is equal to 2. Okay, so that's true. Okay, now assume that p sub k is true, which means that 9 to the k minus 1 is equal to 4c. Okay? So assuming that that's true, if we have p of k plus 1, can we prove that that's true? So we would have 9 to the k plus 1 minus 1 is equal to, let's just see what we can do with this. Okay? 9 to the k times 9 minus 1, right? And okay, we know 9 to the k because we wrote it here. So we can say 4c plus 1 times 9 minus 1. 36c plus 9 minus 1. Okay, but what we need to make, it needs to be divisible by 4. So, okay, this is true. 4 times some integer value is equal to this. We're trying to say that this is also 4 times some integer value. So let's take out a 4 here. Can we do that? 9 times 4 is 36. C plus 2. Well, c is an integer, so this is going to be an integer here. So we can just call this some other integer L. So 9 to the k plus 1 minus 1 is equal to 4 times an integer as well. It's a different integer. So there you go. That's the proof. Okay, now let's do one last example, but using the extended induction principle where you don't have to start at 1. You can start at 10, and for all positive integers greater than or equal to 10, prove something. Okay, and so the example is, let's prove that n factorial is greater than 2 to the n for all positive integers greater than or equal to 4. Okay, so the step 1 is you want to prove p sub 4. At 4, you've got 4 factorial. 4 times 3 equals 12. 12 times 2 is 24. Is 24 greater than 2 to the 4th? Yes. Okay, so I guess what they're going for is like, but if we started at 1, is 1 factorial greater than 2? No. Let's see, what about 2? Is 2 factorial greater than 2 squared? No, it's not. They're equal. But the starting term is 4. The n is equal to 4, and that it is true. So now let's assume that p of k is true, meaning that we're saying that k factorial is greater than 2 to the k. Okay, then knowing that, with that assumption, let's prove that pk sub 1 is true. So k plus 1 factorial is greater than 2 to the k plus 1 power. Okay, the first thing you need to do is say, okay, let's write out that k plus 1 factorial. What is this equal to? it's equal to k plus 1 times k factorial, right? K factorial is always greater than 2 to the k. So what we can say is if k factorial is always greater than 2 to the k, if these are equal and k factorial is always greater than 2 to the k, then this inequality must be true, right? Because if these two are equal and then you have this 2 to the k is always less than k factorial, then this is true. Okay, so we need to adjust this k plus 1 here. We need to change it. Can we say that k plus 1 is always greater than 2? Can we say that? Can we say this? Well, yeah, because, okay, let's simplify it. K is greater than 1. K has to be greater than 1. Well, yeah, it is, because we're only considering greater than or equal to 4. So we can, but in that case then, since k plus 1 is always greater than 2, if we put a 2 here, it will always be for sure less than this. This inequality will hold. Okay, so what do we have? Two. Then there you go. That's what we were trying to prove. So there you go.